Hey, yo, bro, I think the robots are taking over, man.
What do you mean?
I was outside, yeah, and the street lights turned on by themselves. I think they have brains or something.
Are you mad? They don't have brains, they have sensors called LDRs. When the light intensity decreases, the resistance of the LDR increases. That way the LDRs are connected, it means that the lights turn on automatically when it gets dark.
Oh, I bless. I thought the feds were onto me still.
What? Why would feds be onto you still? You're not on road, bro. You volunteer at nursing homes. Your best friend is Boris Johnson's grandma.
Grandma, she's my plug, innit?
The only plug is the plug to her life support, bro.
Oh no, trust. She deals with that substance, bro.
Hey yo, what substance, man? You think you're tough, bro? The only thing that she deals you is Skittles. Here we're going to be looking at some of the more cooler, some of the more complex circuit components that you might come across in your exams. And the first one is a thermistor. And it's denoted with this sort of circuit symbol. What's special about a thermistor is as temperature increases, its resistance decreases. This is because in a thermistor, as temp increases, bonded electrons become delocalized. And if you increase the number of electrons flowing through, you increase the charge and therefore you increase the current. So therefore the current increases, and you know V equals IR. Current and resistance are inversely proportional, so therefore the resistance decreases. Now, you probably don't need to know this explanation in your exam, and they probably won't ask you for it, but it's good to know. What this means is if you look at a resistance versus temperature graph, temperature on the x-axis, resistance on the y-axis, you'll notice it looks something like this. As temperature increases, the resistance decreases. And as temperature gets lower, the resistance actually increases. Now the next component is something called an LDR, and this is almost identical to the thermistor, except the thermistor is to do with temperature, whereas an LDR is to do with light intensity. So in this case, as if you were to plot a light intensity versus resistance graph, light intensity, resistance, you will get the exact same graph, but you just have light intensity. As light intensity increases, the resistance decreases, and vice versa. As light intensity decreases, resistance increases. And you might be asked in your exams some questions where if you're changing the light intensity incident on an LDR, you're changing the temperature on a thermistor, what adjustments would you have to make to a circuit in order to keep the voltages across each component the same? Let's look through an example. Now this is similar to a question that came up in a past A-level or AS level paper. So initially you're told that the voltage reading on the voltmeter is equal to 0. And now that you're told is that the thermistor, the temperature across the thermistor increases. And you're asked to make a change in order to get the voltage reading back to 0. And I'm going to give you a few options, and I'll give you some time to think about which one is correct. I advise you to pause the video and calculate and decide which you think the answer is. Now I hope you have some time to think about that. So let's look through this. So you know that the temperature across the thermistor increases, and what that means is the voltage across the thermistor decreases. So if the voltage across this decreases, this voltmeter is set up so that if the voltage on the right hand side decreases of one side, in order to get the voltmeter back to 0, the proportion of the voltage across Q to R must be the same as the proportion of the voltage of P to the thermistor. Let's call it T. So therefore, if T decreases, in order to keep this ratio the same, you either need to decrease P, because therefore, if you decrease the resistance of P, the voltage reading across P will also decrease. So then they'll sort of cancel out and balance each other. Or if you increase Q, it will increase the voltage on Q relative to R, and because P on its own is usually bigger than T with this new temperature decrease, the voltage reading will go back to 0, or you have to reduce R, and that will also do the same thing as increasing Q. So in this case, the correct answer is to increase the resistance of Q. This way, you're going to maintain the same ratio between Q and R and P and T. There are a couple other circuit components that are worthwhile knowing about, but they aren't usually assessed. One is the semiconductor. And a common type of semiconductor is something called a diode. And it has this circuit symbol. One big feature of a diode is that it's known to only let current in one direction, and that direction is the point in which this sort of triangle is pointing. So you can see it's pointing to the right in this case. So it only really lets current to flow in that direction. And that's because inside this diode there's a tiny vacuum. So that means that electrons would need a lot of energy, so that means a high voltage, to jump the vacuum. So if you were to look at a diode graph in terms of voltage against current, or current against voltage, you'll see it will look something like this. This here is the threshold voltage, or the breaking voltage. Let's call it Vmin. And for a silicon diode, it's roughly equal to 0.7 volts. You'll notice on the other side that it does actually let current through, but the voltage required for this is quite high, maybe around 50 volts. Might be worth having a look at what that voltage is, but you would need a very, very high voltage compared to the voltage on this side to allow electrons to flow through. But you can see here that once you pass that voltage on either side, let's look at this 0.7 volts, once you pass that, the resistance of the diode is very, very small, so it allows a lot of current to flow through. Diodes can be particularly helpful in circuits because they allow current to flow through in one direction, but will help stop it from flowing in the other. As in this case, you need a very high voltage in order to allow current to flow in the opposite direction. The last component is something called a superconductor. And if we look at the graph of resistance versus temperature, for a superconductor, resistance is 0 for a while until it gets to a certain temperature. It shoots up and then increases like that. This here, I want to call it T critical, is the critical temperature. So for a superconductor, it has 0 resistance below a critical temperature, which means that no power is dissipated in this superconductor below that temperature. But as you can see, when you pass that temperature, the resistance increases very rapidly. I advise you to go look at some practice questions in order to help reinforce what you've learned today. It's a good way to understand how to apply the content and the equations. Please make sure to subscribe, like and comment, and feel free to watch any of my other videos if that will help you with your physics course, and good luck for your future.